Hello, everyone, and welcome to another Nortek webinar. Today, we're going to be covering an interesting topic, and that is the use of ADCPs for something other than actual current measurement, and that's the actual estimation of biomass. Now, I kept the original title of the presentation here just for consistency, but it's actually a bit too narrow because in reality, a more accurate and more encompassing description of what we're going to talk about is actually the underwater acoustic imaging, as I'll be talking about more than just biomass, but the image of all sorts of things in the water column, from fish to krill to sediments. So let's get started. Now, you're probably well aware of the basic concept of what an ADCP is, but just to cover the basics, these are instruments that transmit acoustic pulses that propagate through the water column, like is described here in these drawings. And these pulses of sound, they propagate through the water column, and they are received back at the instrument itself, and the ADCP then transforms the signal into water velocity data. We listen at different times intervals, so we effectively slice in the water column into multiple layers, and therefore we create a profile of velocity. Now, a byproduct of this process is that ADCPs also record the strength of the acoustic signal that it receives in the forms of the echoes. Now, these are called by many names, and here I'm going to use the term signal strength, or simply SNR. I'm going to use the term signal to noise ratio, or SNR, which has actually units of decibels. Now, the signal to noise ratio, or SNR, is a function of many things, but the three primary ones are the amount and the type of the particles that are floating within the water column, the distance away from the ADCP itself, and the frequency of the acoustic pulse that is used. And the spatial resolution of these data is a function of the user-defined velocity cell size, because both the velocity and the signal strength come from the same depth cells. So in practice, standard SNR data typically show basic characteristics that I'm showing here, which is this is actually some SNR data from one of our signature 100 systems that was deployed up looking in about 250 meters of water just offshore here in San Diego. And these three characteristics are that the stronger signal is closer to the instrument and decays as you move farther away from the instrument. You can see that the coarse resolution matching the velocity depth cells, so you can't really make out too many details. I mean, you can see coarse structures, but you cannot see many details. And because this is coming from the ADCP's slanted beams, that means that it is susceptible to the side lobe interference, which means that the data closest to the surface here, you're looking at about some 30-ish meters from the surface, are actually not able to be used. Now, wouldn't it be great if we could take this SNR data and increase its resolution, increase the dynamic range, and get this so we can then image the water column more like what it actually is. For example, wouldn't it be great if we could turn this data that we have here in SNR into something more like this, where you can see an unprecedented level of detail of actually what's in the water column, from physical phenomena such as internal waves to high resolution imaging of plankton masses to a variety of sea life and even vessels passing by on the surface. And wouldn't it be great if we have the data be range corrected, so it's independent of the distance away from the ADCP, and the best part, to do this from a single instrument that at the same time is also measuring currents and everything else that an ADCP normally does. Now, I think we'll all agree that this will actually be pretty cool. Well, this is exactly what we at Nortek have done by adding a scientific echo sounder mode to some of our signature series ADCPs. This is a mode that is available on the Signature 1000, the Signature 500, and on the Signature 100. And here on the Signature 100 is actually done by a purpose-built multi-frequency beam that is specially designed for biomass studies. This mode allows for the computation of the scattering volume as well as the target strength for all of these systems, which are two acoustic parameters widely used to quantify what's actually in the water column. The mode also works on the fifth beam, which is the center beam for these systems over here. and so it's not susceptible to side lobe interference. And there's up to 3 separate echograms that can be recorded, each with a different power level, pulse length, and in the case of the signature 100, also different frequency and bandwidth. I just want to highlight some of the basic specs here. Obviously, with the small resolution down to 3 millimeter size, which is just about that big. We had to, of course, increase the number of cells significantly to more than 10,000 cells, so that we could cover the profiling range of each instrument. The echo sounder mode also supports variable pulse lengths as well as a pulse compression scheme, which is a pulse compression is a method that is used to increase the resolution and the SNR with minimum increase in the power consumption. And lastly, for the signature 100, multiple frequencies and both narrow and wide bandwidths are also available. Now, let's put the boring technical stuff off to the side and let's go for some of the fun stuff, which is really where the cool image that we can produce. Now, we'll start with some basic, simple images from fish in Oslo Fjord in Norway. Now, personally, I'm not a biologist, and so I cannot really comment on at length to the behavior that we're seeing here on the fish. But what appears to me is that they seem to be congregating, maybe feeding, and they seem to be doing so at this wavy surface here, which is a density gradient within the water column. The profile on the right is the echogram that is collected at this time here, represented by this dashed vertical line. And so you can see the reflection from the surface and the reflection from individual fish here in these peaks. Now for some warmer climates, my personal preference, and here's some data from the Maldives. This is a school of fish here on the bottom right of your screen. And this seems to be this moving upwards here, as you can see. And this seems to be in response to the swarm of smaller organisms, which is this cloud here that's coming down through the water over time. They seem to have piqued the interest of the fish down below, and the fish quickly swam up to meet or eat them, or they're scattered, hit on the brakes and scattered somewhere else. You can also see, of course, other features like the very clearly detailed small surface waves here. This is the same location as the previous slide collected by the same system, just a few hours later. And this shows a school of manta rays that is swimming past the bottom-mounted sensor. You can see the acoustic shadow created by some of these rays as they are quite large. In some of them, like this one, you can even get the general sense of the shape of the ray itself. Again, very interesting image that you're able to collect. In addition, of course, at the same time, you're also measuring the currents. This is an interesting data set. This is coming from a signature 500. And the fish that I've shown here on the top left of your screen is a very rare landlocked dwarf freshwater Atlantic salmon. And it exists only in a lake in southern Norway. I'll zoom in here so you can see where that particular lake is. Now, this lake was separated from the Atlantic Ocean during the last ice age, and it trapped this particular species of fish inside it. So, of course, it's of great interest to fisheries biologists, and they wanted to track their movements during the spawning season. So they deployed a signature 500 up looking in this frame here. One of our employees, Tom Christian, helped them out with the deployment, and it was around sort of midway through the site or through the lake here. And they wanted to track the movement. So let's take a look at what they were able to see. Now, they deployed the instrument for about 30 days. And here I'm showing just a little over 12 hours worth of data, which was about a gigabyte in size. And right away, you can see the fish mostly congregating towards the top 1/4 of the water column, some venturing farther deeper over here, as you can see. And you also see some pretty detailed density gradients throughout the bottom half of the water column. Now, if we zoom into this area over here, which is about 1 hour worth of data, and you zoom into that, you get to see a much greater detail on the fish themselves. And if we zoom into the top half of the water column, we can see the actual individual fish as they swim past, or they swim past the signature 500. Again, I'm not a biologist, so I'm not sure why the undulating pattern in their fishing behavior. So it'd be interesting if any of the biologists in the crowd might be able to comment on that in the Q&A session. This is another data set also coming from a signature 500 system, this time here in the USA, but this time is from a down-looking instrument mounted on the surface buoy in an large estuary on the east coast of the United States. What I'm plotting here is the echogram data, followed by the standard SNR data, the speed and direction of the water column. Again, all of this collected by the exact same instrument at a twice per second rate. Now, from the speed and the direction data, you can clearly see the tidal regime with the ebb coming in first, then the flood, and then the ebb again. The ebb. And you can also see that this location has a very strong, pronounced vertical shear in the water column. You see, for example, this particular period in time here, you see fairly slow velocity or velocities in one particular location in the middle of the water column with significant faster velocities at the same time farther down in the water column. Now, to me, what's most interesting here is the actual difference in the acoustic response between the standard SNR data collected by the slanted beams and the echogram data that's collected by the center beam, which has a much higher resolution and dynamic range. For example, the cloud of sediment that shows up in the SNR data over here in the first half of this particular data section seems to suggest that this is actually disconnected from the bottom, but we can see from the echogram data that's definitely not the case. And what we're seeing is actually sediment being resuspended as the currents increase, being resuspended and thrown up in the water column, and actually very much connected with the bottom itself. You could even see some finer details of possible sediment being trapped here in the top right of the echogram, with, of course, significantly higher detail than what you're seeing in the SNR data. Now heading back to some colder climates, here's data courtesy of NOAA, where they have used a number of signature 100 units to map the advective biomass transport of the Antarctic krill around the Antarctic Peninsula. Now the data shown here are calibrated scattering volume over here, both in the wideband pulse on the top and on the narrowband pulse on the bottom of the bottom graph. And the red blobs that you see here, just below the surface is this steady line here, the horizontal line at 0 meters depth. These red blobs are actually the Antarctic krill, which is not only a major source for a major fishery, but is also a critical component of the Southern Ocean ecosystem. Here's a zoom into about 18 hours of that data, and here the krill are clearly imaged on the surface and shown here in these areas. And we also see some fish or squid down below. We can even identify individuals in them. We also have some yet to be identified organisms here in about the mid-depth. We don't know what they are. Now, again, remember, because we're doing this and we're also have not just the data from the biomass, but also the currents with the combined ADCP capability, the advective biomass transport has been able to be calculated, which are these red masses flowing out of these black dots, which are the location where each of the 6 moorings with the signature 500 or signature 100 were located. So you can see the advective biomass transport because of that combined capability.